Dear students, welcome to SAIMEDHA Koti Hyderabad. The topic what we are going to discuss now is electrical representation of binary data in PCM. Let me put the subheading: electrical representation of binary data in pulse code modulation, that is in PCM. So what is this topic all about? Let us discuss in detail. Right. Now if you remember the transmitter part of pulse code modulation, what is the first part or what is the first block? The first block is the sampler. And what is the purpose of the sampler? Sampler is used to convert a continuous time signal into a discrete time signal, right? After sampler, the next block is quantizer. And what is the purpose of this quantizer? Quantizer rounds off the sample values to the nearest quantization levels. Quantizer rounds off the sample values to nearest quantization levels, and I hope that you are comfortable with quantization also. After that, the quantized samples are fed to the next block known as the encoder. And remember, this encoder is a to D converter. Encoder is a to D converter which generates the binary data for the samples. Okay, let me write: encoder is a to D converter, means analog to digital converter which generates the binary data for the sample values. Right? How many bits it is generating depends on the system what we are going to use. Right? Suppose if my encoder is a 2-bit A to D converter. 2 bits are generated for each sample, and the name of the PCM system also changes. 2-bit PCM system it becomes. Suppose if I am going to use a 3-bit A to D converter, 3 bits are generated for the sample value, and the system becomes 3-bit PCM system. Assume that I am going to use 3-bit A to D converter. Suppose if I am going to get a sampled value, that is quantized value as a 2. Now it is what is this encoder doing? Encoder generates the binary data for the sample values. Binary data means 3 bits, means how I can write 0, 1, 0 like this. Suppose if my sample value is 3, which is sample value means what? After quantization, if the sample value is 2, 0, 1, 0. After quantization, if the sample value is 3, 0, 1, 1. After quantization means round off values are 2 means 0, 1, 0, 3 means 0, 1, 1, because 3-bit A to D converter, right? Now in general we can represent like this. N-bit A to D converter. N-bit A to D converter means what it will be doing? It will generate n bits for the quantized values. Are rounded off values, right? And look here, and the system becomes n-bit PCM system. N-bit PCM system means the output of the quantizer is encoded into n bits, means n bits are generated for each value that is coming out of the quantizer, right? And after this what we are going to do? The binary data is represented in various electrical formats. See, this binary data has to be transmitted to the channel, no? So what we are going to do is, we are going to represent the we are going to use the electrical representations for this binary data using rectangular pulses, So the binary data is represented in the form of rectangular pulses for transmission. Right. Suppose if I am going to use a scheme known as on-off. Look here, 0 1 0 means 0, this is 0, nothing is transmitted. 1 means a rectangular pulse like this, of which some TB, and again 0 means nothing is transmitted. So these kind of rectangular pulses we are going to use, and we are going to have various kinds of representation, right. So now we are going to discuss what are the various representations we are having to represent this binary data. Hope you are comfortable with this one, right. Fine. So let us discuss the various schemes we are having. The first scheme is on-off. In this on-off signaling also we will call, we have to represent either 1 or 0 in the form of rectangular pulses for transmitting to the channel, right. So if I want to represent a 1, I will use a rectangular pulse like this, of which the TB and voltage some plus V, and if I want to represent 0, so over a bit period TB I will transmit nothing. So this is the representation in on-off signaling. Suppose if I am going to have the next signaling known as the famous signaling scheme non-return to 0, N or Z, or the other name is bipolar signaling. Here also our aim is to represent either 1 or 0, Now 1 means we will use this kind of rectangular pulse for transmitting over the channel. 0 means inverted rectangular pulse, like this for transmitting over the channel, right. So this is the first scheme on-off, this is the second scheme non-return to 0, and we have the third scheme return to 0, RZ signaling. Now how you are going to represent your binary data, either 1 or 0 we have to represent, means digital communication means transmission of 1s and 0s only, no. So, but here for representing 1 in the form of rectangular pulses, if the bit duration is TB, we are not going to make use of the entire bit duration, but we are going to make use of only half of the bit duration, and I am going to use a rectangular pulse of half of the bit duration for 1, and for 0 we will be transmitting nothing. 0 means 0 only, right. RZ signaling. After this comes the fourth one, differential encoding. And here we will try to draw this differential encoding by taking on-off into consideration. See here 1 means, and remember in the differential encoding the representation of 1 and 0 depends on the previous level. Suppose for 1 previous level is maintained, previous level. We will take one example, then you will better understand. For 0, previous level will be toggled, right. So, this is about differential encoding. And fifth one is Manchester. Or this is also known as split phase. Manchester or split phase signaling, in which if you want to transmit 1 or 0, 1 means this kind of rectangular pulse. This kind of rectangular pulse, and 0 means inverted like this. 0 TB, this is TB by 2, TB by 2, right. This is about Manchester or split phase. And we have one more scheme known as, I will write here, sixth one, alternate mark inversion. Alternate mark inversion, AMI. Here we want to represent either 1 or 0. 1 means I will use this one or this one. This also you will understand if you take one example, and 0 means nothing will be transmitted, right. So, this will be plus V, this is minus V. So, these are the different electrical formats we are going to have, and let us see with an example. And before looking at an example, if I talk about the bandwidth, what is the bandwidth of each scheme here? What is the bandwidth of each scheme? For that, I will do one thing. Let us turn this towards the left by some amount. Yeah. So, if you are talking about the bandwidth, you can observe here. See, what is the pulse we are going to use here? All I will do in the next slide. What is the pulse we are going to use? Rectangular pulse. So, remember that suppose if I am going to use a rectangular pulse of width TB, means this is from minus TB by 2 to TB by 2, if I assume, right, and the Fourier transform of this rectangular pulse is sampling pulse, and here we will neglect all the side lobes for calculation of the bandwidth. And remember here the pulse width is TB, no? Reciprocal of this pulse width is RB. So, the first null, this is the first null. So, first null is nothing but the reciprocal of this pulse width, this is minus RB. So, that here bandwidth will be highest frequency minus lowest frequency for positive frequencies. So, if I am going to use a rectangular pulse of width TB, bandwidth will become RB hertz. Hope you are comfortable with this one. And here based on this, on off if I take, what could be the bandwidth? Rectangular pulse of width TB I am going to use. So, bandwidth will be RB hertz. Non-return to 0, bandwidth will be RB hertz, isn't it? Now, third one, here I am going to use a rectangular pulse of half of the width, no. So, compression in time domain is equal to expansion frequency domain. So, opposite effects takes place, no. So, bandwidth will be 2 RB hertz. 2 RB hertz here, 2 RB hertz. And coming to differential encoding, so on off I am using means bandwidth is RB hertz, and after this Manchester. Here in Manchester, if you observe, see here the main component is half width rectangular pulse. If I know this one, I can form this one also, right? So bandwidth is 2 RB, 2 RB, and here bandwidth is RB, RB hertz, RB hertz. Now by looking at all this, can you frame a relationship between this bandwidth? Yes, I can make that. Look here, how I am going to make the relationship with the bandwidths. You can observe here. Bandwidth of on off, bandwidth of on off is equal to bandwidth of NRZ, bandwidth of NRZ is equal to bandwidth of differential encoding, which is equal to bandwidth of AMI, bandwidth of AMI less than, this is less than bandwidth of RZ, which is equal to bandwidth of Manchester or split phase, Manchester. I can write like this. Can I write like this? Yes, I can write the bandwidth relations. Now let us take an example and verify. Suppose if I have an input bit, the output of the encoder is like this: 1, 0, so 1, 0, 1, 0. How we are going to represent this binary information in different electrical formats, what we discussed. So here let us draw dotted. This is the output of the encoder. So first scheme, this is a 0, this is a TB, 2 TB, 3 TB, 4 TB, 5 TB, 6 TB. Now the first scheme, what I am going to use, on off, on off. In on off, how we are going to represent 1 and 0? 1 means this kind of rectangular pulse, no? This kind of rectangular pulse. 0 means nothing. This is some plus V volts. 1 means again this kind of rectangular pulse. 0 means nothing. 1 means this kind of rectangular pulse. 0 means nothing. This is on off. Next is non-return to 0. Non-return to 0 or bipolar signaling. Non-return to 0 or bipolar signaling. 1 means this kind of rectangular pulse. 0 means this is plus V, inverted rectangular pulse. This is minus V. Again 1 means this rectangular pulse. 0 means this one. 1 means this one. 0 means this one. Non-return to 0. After this, return to 0. Return to 0. return to 0, this is 0, this is TB, this is 2 TB, 3 TB, 4 TB, 5 TB, 6 TB. So here in this return to 0, we are going to make use of half width rectangular pulse only, right. So like this, 1 means this kind of representation, this is TB by 2, 0 means 0, 1 means again this kind of representation, 0 means 0, 1 means this kind of representation, 0 means 0, like this, return to 0. After this, differential encoding, and let us use on off as the scheme. Now as I told you that in differential encoding the output depends on the previous level, the output depends on the 5 TB, 6 TB. So assume that previous level is 0, assume that previous level is 0. Now how we are going to get the output in differential encoding? 1 means previous level is maintained, 0 means previous level will be toggled like this, 1 means previous level will be maintained, 0 means previous level will be toggled, 1 means previous level will be maintained, 0 means previous level will be toggled like this, right. This is differential encoding. Now if I go for the next scheme, Manchester or split phase, Manchester. Now what will happen? 1 means this kind of rectangular pulse, 0 means this one, again 1 means this one, 0 means this one, 1 means this one, 0 means this one, right. So this is regarding Manchester, and we are left with the last one, which is nothing but AMI. So alternate mark inversion, 0 TB, 2 TB, 3 TB, 4 TB, 5 TB, 6 TB. Now observe here, first one is 1, means this kind of rectangular pulse we are going to use. Second one is 0, 0 means nothing. Again 1 means as we are using this one for the previous one, now inverted of this rectangular must be used, right. Again 1 0 1, again 0 means nothing, again 1 means now I am using this one also, inverted of this one, 0 like this, 1 0 1 0 1 0. So in this way we are going to use different electrical formats for representing the binary data. And here, dear students, remember that whenever you are using this kind of representation using rectangular pulses, we are going to have a serious problem. We are going to have a serious problem known as inter-symbol interference. What is that? Inter-symbol interference, which we will be discussing in the next part. And I hope that you understood this concept of electrical representation well. And for more details, and if you want a good discussion on the entire subject, please contact SAIMEDHA, Koti, Hyderabad. Thank you.